All right, it is 10:31. We should get going. So last time we talked a little bit about antiderivatives. We're going to use a little bit more, and then we'll move on to talking about area under a curve. This example here, this is just another way of phrasing find the antiderivative, right? I told you what the derivative of f was. I'm asking you to find the actual function f of x. So we're going to antidifferentiate each of these. And just like last time, we're going to remind ourselves that if the derivative, not the antiderivative, if you were to take the derivative of any of these functions and it makes you multiply by a constant, the antiderivative, you end up dividing by that same constant. So I know, thank you, if we were to take the derivative of e to the 2x, we would get e to the 2x multiplied by t. The antiderivative is going to be whatever the antiderivative is divided by t. 2, not t, 2. So here, the antiderivative of 8 e to the 2x is 8 e to the 2x divided by 2. Because the derivative of e to the 2x, you're going to multiply by that 2, and they're going to undo that division. Same deal here. We know that the antiderivative of sine of x is negative cosine of x. So the antiderivative of sine of 3x is going to be negative cosine of 3x, and then we have to divide by 3. So we're going to get plus, fine, I should have written minus sign, plus 6 times negative cosine of 3x divided by 3. Same deal for secant squared. We know the derivative of tangent is secant squared of x. So the antiderivative of secant squared of 4x, we have to divide by a 4. So we're going to get tangent of 4x divided by 4 and plus c. I would say this to me, this looks absolutely terrible. So I would simplify this as 4 e to the 2x minus 2 cosine of 3x plus 1/4 tangent of 4x plus c. This is a very, very common thing that happens where if the derivative via the chain rule would make you multiply by a constant, the antiderivative makes you divide by that same constant. Questions about that? If you can grab this here. Yeah, I'm trapped. Jennifer? Yes, but I should say it's a very narrow type of function. If, for example, in fact, I'll say, so if on the other hand, I said like your function was, if your derivative was sine of x squared, that idea doesn't work for finding the antiderivative. In fact, this function is kind of famously not antidifferentiable. There is no nice function that isn't antiderivative of sine of x squared. So it doesn't work if your inside or your argument of your function is more complicated than just a multiple of x or a multiple of x plus c. And then to answer the second question here, if we're told that the initial condition is that the function's equal to 5 when the input's equal to 0, or f of 0 is equal to 5, we want to find the value of the constant there. So we're just going to plug in 0 for x and set it equal to 5. So f of 0 is going to be, and this is our f of x here, 4 times e to the 0 minus 2 times cosine of 0 plus 1/4 times tangent of 0 plus c, and that should equal 5. So now we need to know, whoops, sorry, I shouldn't do that. E to the 0 is 1. Cosine of 0 is also 1. Tangent of 0 is 0. So it looks like we have 2 plus c equal to 5. So c is equal to 3. And if you were asked to, we would say that so this function here is the particular solution to this differential equation, right? I should point out this is a differential equation. When you have a derivative equal to something and you're finding the original function, that's an example of a differential equation, which we'll definitely see when you take 17C. Yeah, 17C. Or actually, maybe like I always forget which content is in which. It might be later this quarter we talk about differential equations. Apologies if I misspoke there. I'm thinking 16C is what has the beginning of the quarter with differential equations. Anyway, so we solved this differential equation and we found the general solution, right? This is a family of solutions here where C could be any constant. But then we were given an initial condition and we found the particular solution. Well, actually, we didn't write it down. The particular solution here would be the same function with that value of C plugged in. So f of x would be 4 e to the 2x minus 2 cosine of 3x plus 1/4 tangent of 4x plus 3. That's your particular solution for this particular initial condition. Cool. I should say generally, for those of you new, you're always welcome to ask questions, interject, or if something is not very clearly written on the paper or I'm off screen like that, just let me know and I will adjust. But also please do feel free to ask questions. Thanks. Can't be done. All right. I feel like I should give one more example of a problem like this, specifically with I wrote it down here earlier, with kinematics or motion. So let's say we're given the following situation. We're given a ball is thrown upwards with an initial velocity of, let's say, 80 feet per second. This kind of question, I feel like there's a pretty standard set of things we ask. Usually there's two questions we ask. We often ask, what is the maximum height of the ball? Maximum height the ball reaches. And we also ask, how fast is the ball going when it hits the ground? But to do any of this, we have to kind of derive the equations for position and velocity. Given that the acceleration of a body in motion due to gravity is negative 32 feet per second squared. I'm going to leave off the units and just write negative 32. So that means every second, the velocity downward increases 32 feet per second. So like if a ball were to just be dropped, a second later, it'd be traveling at 32 feet per second, ignoring any kind of air resistance. Another second later, it'd be traveling at 64 feet per second, and then 96 feet per second until you reach terminal velocity. We don't worry about the physics of things. We're just the math. We're just looking at the math. So we're given this, and we want to find first the velocity. And it's important that we know that the derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration function. If you think about it, position, which we usually think of as either S of t or h of t, I'm going to write h of t, height is measured in this case, feet. And if you take the derivative of that, or the rate of change of that position, you get velocity. You get v of t, which is the derivative of position, which is measured in feet per second. And if you take the derivative of that, or the rate of change of velocity, you get acceleration. Which I'm probably spelling wrong, not in spelling class. Acceleration, which is the derivative of velocity, which is the second derivative of position. And that's measured in feet per second, or how fast the velocity is changing. People usually write feet per second squared, but it's equally correct to write feet per second. It's actually, I feel like it makes it make more sense if you write feet per second, because you're asking, how is the velocity measured in feet per second changing every second? Okay, all that aside, go ahead. Downward. Well, good question. So I would say that it's 32 downwards, it's negative 32 upwards. So if I'm saying it's negative 32 upwards, that means it's going down because I have a negative. So the negative kind of indicates the opposite of what we think of as the positive direction. Mm-hmm. Yeah. I would, yes. But so people do it differently is the problem. Some people like to do it. We change our frame of reference depending on what we find convenient for ourselves. It is fairly standard to think of it as negative all the time. Although it's certainly, some people do think of it as positive and write it that way. So it depends, is the unfortunate answer. Nope, still be negative. The initial velocity is going to be positive, but the acceleration is still negative. Because if you throw it upwards, is the ball going to get faster or slower? Slower, right? So it's going to decrease its speed. So let's go ahead and find the velocity by anti-differentiating the acceleration. So I don't know if we've talked about this, but whenever you're anti-differentiating a constant, you just get that constant multiplied by whatever your variable happens to be. In this case, we're using t. So our antiderivative here is going to be negative 32t plus some c. That should be legit, right? If you take the derivative of negative 32t, you're going to get negative 32. The derivative of a constant is 0. But we want to figure out what that constant is. Well, we know something. We know that the initial velocity at the moment we throw it is 80 feet per second, which is pretty fast. So that means that if we plug in 0 for t, it should equal 80. So that constant there, which is just the initial velocity, is going to be 80. So we get that c is equal to 80, and our velocity function is negative 32t plus 80. So when we throw it, the ball is going 80 feet per second, and then a second later it's going 58 and 48 feet per second, and a second later it's going 16 feet per second, and a second later it's going negative 16 feet per second. So at some point between like 2 and 3 seconds, it's going to change directions and start going downwards. I still think we should find the height function before we do anything else. So let's find the antiderivative of velocity to find the height function. So the height function here is going to be the antiderivative of that, so it's going to be negative 32 times t squared divided by 2 plus 80 times t plus another constant. I like to use a different letter even though c is already been taken care of. Let's call it k. I should point out, typically, the way this always works out for these kind of motion problems is that constant there is just your initial velocity, which we label as v naught. And this constant here is just going to be our initial height, which is h naught. What is the initial height of the ball? I know I didn't say it, but we're throwing it, right, we're throwing it from the ground unless we say otherwise. So our initial height is 0. So when we plug in 0 for t, we're going to get negative 16 times 0 plus 80 times 0 plus this constant equal to 0, which is going to mean that that constant is equal to 0. So our height function is negative 16t squared plus 80t, and that's it, plus 0. But I'm not going to write plus 0. And yeah, I should say, no. Generally here, your velocity function is always going to equal negative 32t plus v naught if you're measuring in feet per second, right? If you're using other units, it's different numbers. And your height or position function is negative 16t squared plus v naught times t plus h naught. So now we have all the things we need to answer the questions that were posed. So the first question is, what is the maximum height of the ball? So we're trying to maximize the height function. And we learned last quarter that to maximize or minimize a function, we want to find the critical value. We want to take the derivative, which we already have, it's the velocity function, set it equal to 0, and then find out when we're going to have maximum, which makes sense, right? If the ball is going upwards, its velocity is positive. And then if it's going downwards, its velocity is negative. And to go from positive to negative, you had to go through 0. So that's where the ball is going to have a maximum height when the velocity of the ball is 0. It's neither going up nor going down for one brief moment in time. So we're going to set the derivative of height, which is just velocity, over here, equal to 0. And solve for t. So negative 32t equals negative 80. T is going to equal 80 divided by 32. And both of those have a factor of 8. So that reduces to 10 over 4, which is 5 over 2, or 2.5. Which is not surprising, right? We just talked about how the ball was going upwards at 2 seconds and downwards at 3 seconds. So somewhere between 2 and 3 seconds, in this case, exactly the midway point, the ball is going to top out. So the time of maximum height is 2.5 seconds or 5 half seconds. We're not done though, right? That doesn't actually answer the question. That's telling us when we reach a maximum height, but the question was, what is the maximum height? So we have to take that value of time and then plug it into the height function to find what the maximum height is. So the maximum height occurs at time equal to 5/2 seconds. So then we're going to plug that in. We say height at 5/2 is equal to -16 times 5/2 squared plus 80 times 5/2. This simplifies pretty nicely. It's going to be -16 times 25/4 plus 80 times 5/2 is just 40 times 5. So we can cancel a 4 here and a 4 here. -4 times 25 is -100. 40 times 5 is 200. So we're reaching a height of 100 feet. That is the maximum height of this particular ball thrown at this velocity. Seems pretty high. I don't think I can throw a ball that high.
Why did you not set the position equation to 0? Why was it the velocity?
So if position is equal to 0, that means the ball is on the ground. And the first question here, not the second question, the first question is, what is the maximum height the ball reaches? So I'm trying to find when the ball reaches its apex here, and that's exactly when the velocity of the ball is equal to 0. What I'm really imagining though, is like I've thrown the ball like this, and I'm really looking for this point here. And last quarter in 17A, we talked about how when you're trying to find the maximum or minimum of a function, you're setting its derivative equal to 0 to find that place, right? Because if you're maxing out there, your tangent line is a horizontal line. But as you perfectly led into the next part, we're going to set the height equal to 0 to find when the ball hits the ground. So we're going to set h of t, which was -16t squared plus 80t, I believe, yeah, equal to 0 to find when the ball hits the ground. Okay, so this factors nicely. I can factor out a t, and actually I can factor out a 16 as well. So this factors as 16t times -t plus 5. So either we're going to get time equal to 0, which is not when the ball hits the ground. It's when we threw the ball, so it's not that. Or time equal to 5 seconds. So after 5 seconds, the ball will hit the ground. And this is not terribly surprising because we started at the height of 0, we're ending at height of 0. So it's kind of a perfect parabola where it's going to travel upwards for the first 2.5 seconds and downwards for the last 2.5 seconds. So it's very symmetric here. I think that happened last time too. Maybe this is just the time when whatever that is turns on. So then we're going to find the velocity at that 5-second mark when it hits the ground. So the velocity there, let's see, the velocity function was -32t plus 80. So this is going to be -32 times 5 plus 80. 32 times 5. Quick trick for multiplying by 5 is multiply by 10, then divide by 2. So -32 times 10 is -320, divided by 2 is -160. It's going to be -160 plus 80, which is -80 feet per second. And the velocity should be negative here because the ball is traveling downwards, so it makes sense. Not surprisingly, or at least not surprisingly to me, the downward velocity is exactly the same as the velocity we threw the ball at in the beginning, because again, there's this very nice symmetrical thing that happens where we threw it up with speed and it comes back down with the same speed. Question.
So I thought it was asking how fast we will hit the ground. So I thought whenever it says fast, that means speed. And I know that's like
that's a fair point. So I would I should either amend my question and say what velocity is the ball striking the ground with, or I should change my answer and say the speed the ball hits the ground at is positive 80 feet per second, because you're indeed totally correct. Speeds are always measured in a positive way. We don't care about the direction. Later on, when we talk about vectors at the end of the quarter, that idea will come back into play, where we care about direction and magnitude or length or speed. Other questions about this? Yeah, let's get that way. Okay. All right. So moving along, we'll talk about area under a graph. And let's see. It's not high enough space up here, which is unfortunate, but we'll live. Just trying to keep things in order here. Oh yeah. Actually, no, we'll do that tonight. Sure. I have a cool. So I posted something neat in Canvas that I think is very useful for everybody. I'll show it to you in area under a graph. So this point in the game, the idea really is we're just trying to estimate the area under a graph in a typical way. So let's look at the following example. We're going to estimate the area under f of x equal to the square root of x from x equals 0 to x equals 16, which are very convenient numbers. And we're going to use 4 rectangles. And we're going to do it with right endpoints first and left endpoints second. So using right endpoints. So here's the general basic idea. We're going to draw the graph. Your usual square root graph, it looks like this. And let's say 16 is right here. So we're going to break this interval from 0 to 16 up into 4 equal width subintervals, or whatever the number is, right? In this case, it's 4. It could be whatever number we like. So, and let's see, I want to make sure I'm being very kind of specific here. Yeah. So let's talk about the width of each of our rectangles, or each subinterval, is going to be, we usually call it delta x, and it's going to be the entire width. I could zoom in a bit. I can also try to write it bigger. The total width, which is 16 minus 0, divided by the number of rectangles, the number of subintervals, which in this case happens to be 4. The more general formula here is delta x equals b minus a divided by n, where a is your left endpoint, b is your right endpoint, and n is the number of subintervals. So then each subinterval has a length of 4 or width of 4. So we're just going to mark this off, labeling those values. So 0 plus 4 is 4, 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16. So those are my 4 subintervals. And then we're going to kind of section them off here. So we're trying our best to estimate this area. In this case, each subinterval, we're going to draw a rectangle using the right endpoint of that subinterval. So for this first subinterval, we're going to use the right endpoint 4, and we're going to find the function value at 4 and use that for the height of the rectangle, which is clearly going to be an overestimate. So if we start writing our approximation for the area, it's going to be approximately the first width, which is 4, multiplied by the first height, which is the square root of 4. That's your base, that's your height. The second rectangle, so again, same base, but now the height's going to be the height I get when I plug in 8 and get that height for the height of the rectangle. So it's still a base of 4, but now a height, which is the square root of 8. Because again, and I should write this down here, my function here is the square root of x. Continuing along, the next rectangle, still a base of 4, but now a height of square root of 12. And finally, the last rectangle here, base of 4, height of square root of 16.
Why?
Sure. So, well, I would say the heights aren't 12, 16, and 8. The heights are respectively the square root of 4, the square root of 8, the square root of 12, and the square root of 16. Because if I plug in 16 to my square root function, it's going to give me a value of square root of 16, which is 4. So that is literally the height right there. Over here, square root of 4 is 2. Over here, it's not as nice. It's square root of 8. Over here, it's square root of 12. But we're plugging in this. So in this subinterval, we're plugging in this right endpoint because we said right endpoints, right? Not for any good reason other than we decided we were going to use right endpoints this time. Also, right endpoints are usually the most convenient. And then we would calculate this. It's going to be approximately equal to 49.17. Question. You know what? I said 16 and I wrote 12. I'm sorry. Thank you. Good call. In this case, it's clearly an overestimate because our rectangles are encompassing more area than the area under the curve. Let's talk about more so I should point out the general vibe here is that we would say that the area is approximately your base, which is delta x, times, so usually when we're labeling these endpoints of each of the subintervals, we typically label this first one as x sub 0, and then this next one is x sub 1, x sub 2, x sub 3, and the last one should be x sub whatever the number of subintervals is. So x sub n for the very last one. So the area, very generally using right endpoints, can be thought of as the base times the height of the first one, which is f of x sub 1, plus the base times the height of the second one, which is f of x sub 2, plus the base times the height of the third one, which is f of x sub 3, plus the base times the height of the last one, which is f of x sub 4. Which is a terrible pain to write, especially if you have more than 4 things. So this is where we use and why we've talked about sigma notation. I would rather write the summation of things more compactly. So we can also write this as the sum from I equals 1 to 4, because we're adding up 4 things. So I should go through 1, 2, 3, 4 of our f of x sub I times delta x. That's exactly the same expression, just written more compactly. And then we could do it using left endpoints. It gets a bit tedious. We'll try not to be too tedious with it. So if we're doing left endpoints, let me zoom back up. Let's see that picture there. So left endpoints, same idea. Our area approximation would be, well, now instead of using 4, 8, 12, and 16, we're going to use 0, 4, 8, and 12. So it's going to be approximately my base. Now, I should point out here, the base is the same every time. We can factor out the base, right? We can write this instead of as 4 times something plus 4 times something plus 4 times something plus 4. We can say it's 4 times all the heights added together. So the first height is going to be f of 0. The second height is going to be f of 4. The third height is going to be f of 8. And the last height is going to be f of 12. I was going to draw a picture here because we should, sure. I'll draw it up here. So using left endpoints, here are our rectangles. The first rectangle is kind of uninteresting because it's got a height of 0. Second rectangle, there's your height. The third rectangle, there's your height. The fourth rectangle, there's your height. So this red area is our approximation of the area under the curve using left endpoints. Clearly an underestimate here. Quick comment. I don't want you to assume that a left is always an underestimate and a right is always an overestimate. It's not the case. It is the case if your function is increasing like this. But if your function was decreasing, it would actually be the opposite case. And if your function is doing something like this, then you don't really know if it's an over or an underestimate. So here, this would be approximately 4 times the square root of 0 plus the square root of 4 plus the square root of 8 plus the square root of 12. which is approximately equal to, what do we got here? 33.17. So clearly a pretty wide gap between our overestimate of 49.17 and our underestimate of 33.17. In fact, a gap of exactly what, 16? That seems like, oh yeah, a gap of 16, 4 times 4. Okay. Because right here, the only difference really was this term versus this term, and that term is exactly 16 large. So yeah, a gap of 16. How could we make our estimate better? More rectangles. So while I could draw more rectangles, I don't really want to. And I don't think there's a lot to be valued at. But what I do want to show you, really don't love sitting down here, but I'm going to sit down for a second so I can more easily use my computer, is something I just posted in Canvas for you all, which I think is useful. Where'd you go here? Not you. Sorry. I'll just find it over here. It's this Riemann sum visualizer tool, which I think is nice. So if you want, if you're trying to like visualize a Riemann sum, you can, first of all, plug in whatever function you like. So I think it's square root of x and hit enter. And then it gives you the function. And then you can change everything. So we can zoom in and out, maybe. Yes, you can zoom in and out. And you can change your interval to be, in this case, from 0. Whoops, I had 0 there. If you get close enough to a value, it'll kind of lock onto it to 16. Let's make sure we're really at 16 there. Yep, oh, not quite. There we go. Sorry, I know it's kind of wonky. Make sure we're really at 0 as well. Okay, let's see here. Yep, seems good. Okay, so then, oops, zoom out, James, not in. Get our window looking pretty good here. So then what you can do is over here on the left, which I'm in the way of, you can either use, well, you can change the number of subintervals. So we were doing 4, which is not very many. And then you can either, and look, so with right endpoints here, overestimates, our estimate is 49.17, which is what we got. Or we can shift it over here to left endpoints. Oops, why? That's weird. Why? I've never seen it do that. That is interesting, as unexpected. I don't know why it's doing that. It seems really strange. I'm very confused as to why it's doing that. I don't know why. Apologies for not knowing what's going on here. That seems strange. I don't know. Yeah, I'm sorry. I don't know why the left endpoint, the very left, is just like, nope, not going to do it. Yeah, I'm confused. Anyway, so it's usually a very useful tool, except for in this one moment, apparently. You can also use midpoints. The midpoints do kind of, there we go, right there, which will give you a different estimate. And then, as we were talking about, I don't want random. That's okay. Sorry, this seems like it's very wonky today. I don't know why. Usually, I don't know. And then using right endpoints, since those seem to work, we can then increase the number of intervals. Okay, if I use 50, so 50, it's hard to get it to be exactly what you want it to be. We get a much better approximation, if I will look at that, of what the area under the curve is. And if you go, so the real idea here is that to find the actual area under a curve, we can take the limit as the number of subintervals gets infinitely large. So if you go further and further and further, like, you can't go to infinity here, but I think 100, right? You get very close to the actual area under the curve. This is estimating to be 42.8. And notice here, and Dedell was saying this in class yesterday, that when your number of subintervals gets really, really large, it doesn't really matter if you're using left, right, or any old point in the middle, because the difference between them is so minuscule. If we zoom in here, zoom in, James, you can see that, oh yeah, it really doesn't matter if I'm using a right endpoint here or a midpoint, right? It virtually doesn't change the picture at all. We're still using a bunch of rectangles that are all pretty much having the same heights as they had before. So that's why he was saying you can use left or right or any point in each subinterval to get the estimate. And then as you let the number of subintervals get larger and larger and larger, that estimate becomes exact. Questions about, so, and again, this is posted in Canvas. I encourage you to play with it. I think it's useful. It feels like it's acting a little bit wonkily right now, but it's usually very useful. questions about this before we continue? Okay, let's see here. Yeah. Yeah. So that's an excellent question. There's a couple different ways you could do it. I would say yes from 1 to 4. So let me move my picture back over here. Sorry. So, and yes, I would say the standard way is to do it from 1 to 4. So if I was writing the summation here for the area approximation, it'd still be the sum from I equals 1 to 4. But now, instead of f of x sub I times delta x, it's going to be f of x sub I minus 1 times delta x. Let's actually write it out and see what happens. So if I plug in I equals 1, I'm going to get f of x sub 1 minus 1. So that's going to be f of x sub 0 times delta x. If I equals 2, I'm going to get f of x sub 2 minus 1 times delta x plus f of x sub 3 minus 1 times delta x plus f of x sub 4 minus 1 times delta x. So it exactly works out, right? This is when I equals 1, I equals 2, I equals 3. So guess. Yeah, I had all these other examples here. So I do feel, oh yeah,
Problems with n over 2, and they're basically using summation, but they have the limit in front of it, and
Right.
it's like, plug it in and not solve it, and the answers had like eyes and stuff. And I was
which,
like,
do you have a specific example?
yeah, I can show you actually. Like this one, and then even this.
And so they're asking you just to kind of write the area as a limit?
Yeah, but this was the answer.
Okay. Sure, we'll look at it.
Okay.
So this is all to say that the idea that we're working towards is if you have kind of any function. Yes, I can. Or yes. My still function there. And we're trying to say estimate the area. Again, we're still talking estimation for just a second. So the area estimate using n subintervals. So I'm breaking this up into 1, 2, 3, dot, 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 n subintervals. So this leftmost point is x sub 0, that's x sub 1, x sub 2, x sub 3, all the way till the very last one is x sub n. The second to last one is x sub n minus 1. I'm going to think about drawing all those little subintervals and then typically using right, again, not for any other reason other than it's the easiest. So I'm going to use right endpoints to then say, okay, well, this rectangle has that height. This rectangle has that height. This rectangle has that height. This last rectangle is a little bit of an overestimate. So before it would be a little bit of an under. So using all those rectangles, we're just going to app the areas. Here's the long way of writing it. It's kind of a pain. It's going to be, oh, I forgot to say, our delta x here is the total width, or width is the right word, b minus a divided by the number of subintervals, which is n. We usually don't write this unless we have to. We usually just write delta x. But when we say delta x in this context, we all understand it to mean the total interval length divided by the number of subintervals. So then our area here is going to be, well, it's going to be the base times the first height, which is f of x sub 1. Plus the base times the second height, which is f of x sub 2. Plus all the way till the very last rectangle, which is the base times the last height, which is f of x sub n. Nobody wants to write all that. So we're going to say, we could also write it as the sum from I equals 1 to n of f of x sub I multiplied by delta x. This is our approximation using right endpoints. And just to kind of fill in the picture, if you wanted it using left endpoints, the only thing that would change would be that the x sub I would be x sub I minus 1. Sorry, minus 1. So then we want to actually calculate the area. We're going to let, as we said before, the number of endpoints get larger, or sorry, the number of intervals get larger and larger and larger, or go to infinity. So, paper move. Calculate the actual area under a curve in kind of the most numerically, what's the word I'm looking for? Using a lot of typically intense arithmetic and, you know, like there's a lot of actually calculation involved. It's kind of the worst way to do it, but it's the first way to do it is the following. We say that the area under the function f of x on the interval from a to b is given by the following. So area, we typically write it using this integral notation from a to b. It's always from the bottom to the top of your function is equal to the limit of that estimate up there, which you can't quite see. The limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. I believe he gave that definition in class. Technically, you could use left endpoints here, or midpoints, or really any kind of point in each interval you want to, but right endpoints again is standard because it's the easiest to calculate. So then you might get asked a question like, write an expression using limits and sigma notation for, they can either just give you the integral or they can say for the area under the curve between these two, but it's easier just to write the integral. So let's say, for example, for the integral from 2 to 7 of x squared plus sine of x. So your job is to translate this into that. And there's really there's some nice correspondences, correlations here. So this is your function. That's your f of x. In the sigma notation, it's going to be f of x sub I. So the x has to change a little bit. Sorry, I can see people. It's x squared plus sine of x. Sorry, I know. So that's going to be our f of x. We have to identify a couple things for this. So we need to know what our delta x is, what our x sub I is, and what our f of x sub I is. Those are the three things we really need to make this work. Delta x is usually the easiest because delta x is just your total length of your interval, which in this case is 7 minus 2 divided by what? How many subintervals are we always assuming we have? N. Just n. It's always n. Unless it's actually an example where like using this many subintervals. So our delta x here is going to be 5 over n. I do find it helpful in problems like this to actually not draw the whole function. I don't think I need to draw the whole function. Plus, I don't know how to draw that function. It's terrible. I mean, I could maybe figure it out, but really to draw what's happening on the x-axis. So we're going from 2 to 7. And I know that my leftmost endpoint is x sub 0. My rightmost endpoint is x sub n. And then each subsequent endpoint is a width of delta x from the previous one. So if I have, like x sub 1, x sub 2, x sub 3, and so on, my x sub 1 is exactly delta x away from x sub 0. So my x sub 1 is exactly x sub 0 plus delta x. So x sub 1 is my x sub 0 plus my delta x. And then my x sub 2 is also a delta x away from the previous one. So I like to think of it as x sub 2 is x sub 1 plus delta x, but that's kind of annoying. The more typical way to say like x sub 2 is 2 delta x's away from the initial spot. So x sub 2 is your initial 2 plus 2 delta x's. And then a pattern starts to emerge. X sub 3 is your initial spot plus 3 delta x's. And you might just say more generally that x sub I, if you move I intervals or I delta x's away from the initial thing, is exactly the initial value plus I delta x's. So it's 2 plus I times your delta x. I always like to check to make sure I've done the right thing. So it should be true that if I do this, if I add on my delta x n times, I should get to 7. So if I check here, x sub n, yes, sorry, I was like, yeah, I forgot to go ahead. Apologies. So my x sub n, if I plug in n for I, is 2 plus n times 5 over n, but the n's cancel, and I get 2 plus 5, which is 7. That checks out. So this formula here tells you the right endpoint value of any ith subinterval. The first subinterval, the right endpoint is 2 plus 1 times 5 over n. The second subinterval, the right endpoint is 2 plus 2 times 5 over n. The ith interval, the right endpoint is 2 plus I times 5 over n. Great. And then the annoying part, you take that and you jam it into the function that you've identified in the area thing here. So my x sub I don't need to write it again, but my f of x sub I, I'm going to take x squared plus sine of x and rewrite it as x sub I squared plus sine of x sub I, which then really super annoyingly is going to be all of this 2 plus 5i over n squared plus sine of 2 plus 5i. I simplified the I times 5 over n to 5i. Okay, we're almost done. Of course, I've run out of room on the page. So we've got all the pieces now. We've got our delta x, we've got our f of x sub I. We know everything here. So then we're going to say the integral from 2 to 7 of x squared plus sine of x dx is equal to the limit, as n goes to infinity, of the sum from I equals 1 to n. This part's always kind of exactly the same every time. And then here you're going to have your f of x sub I, which is going to be our gross thing here, our 2 plus 5i over n squared plus sine of 2 plus 5i over n. 5i over n. Sorry, it's terrible looking. All of that multiplied by our delta x. So the delta x and the dx are kind of playing the same role. They're kind of like the width of your subinterval, and the f of x and the f of x sub I are playing the same sort of role. So that's how you go from an integral to writing it as the limit definition of the area under that curve. And that's what that is. That is the limit definition of the interval, is how people often refer to it. Any questions about that before we jump into another example?
Basic formula.
Yes.
2 plus I 5 over n.
I would say, yeah.
Yeah. Where did 2 come?
The 2 came from the lower limit of the interval.
Oh.
Sorry, we were starting at 2. So then the next one was 2 plus a little bit, and the next one was 2 plus twice a little bit, and then thrice a little bit, and then 4. Right.
So it changes.
Right, but I should point out, so let's actually talk generally for a second here. So if we're given that you have the integral from a to b of f of x dx, and you want to write the limit definition of the area, we get that the same thing, which I love writing the same thing again, is equal to the limit as n goes to infinity of the sum, I equals 1 to n, of f of x sub I. But let's be a little more specific here. Your x sub I. So up here, sorry, I'm not all over the place here. Up here, your x sub I ends up being 2 plus I times 5 over n. Or more generally, your lower limit value, your a, plus I times your delta x. So that's what x sub I is more generally. It's a plus I times delta x. Where again, your delta x is b minus a over n. So what we're going to write here is f of a plus I times delta x, right? Swapping f of x with f of x sub I. And then multiply by delta x. And then you actually fill in that delta x is whatever it is. It's 5 over n or something over n. So let's go back. I don't remember exactly what it was, but can you read to me what the example you were looking at was?
Yes. It was f of x equals x cosine x,
Mm-hmm.
and then it was from 0 to pi.
Cool. So we want to write the limit definition for the area under f of x equal to x cosine of x on the interval from 0 to pi over 2. All right, same sort of deal. We got to find 3 things. We got to find delta x. Okay, delta x, no big deal. Delta x is our b minus a over n, which in this case is pi over 2 minus 0 over n. I would choose to write this as pi divided by 2n. That seems like the simplest way to write it. And then I used to have a hard time remembering the formula for x sub I, so I would often like write out the first few terms. Like again, I would do this whole thing where I have my number line and go from 0 to pi over 2, and then be like, okay, so there's my x sub 0, and then my x sub 1 is going to be, well, I'm just adding on a delta x. My x sub 1 is 0 plus pi over 2n. And then my x sub 2 is going to be 0 plus, sorry, terrible, 2 times pi over 2n. And so on and so on. So I can start seeing that, oh yeah, x sub 0 is 0, x sub 1 is 0 plus a delta x sub 2 is 0 plus 2 times delta x. So it's looking like all this is leading me to say that my x sub I is 0 plus I times delta x, which I shouldn't be writing 0 plus anymore. That's just going to be I times pi over 2n. Or probably more nicely written as pi I over 2n. Cool. We've got the x sub I. We know the function is x cosine x. So then my f of x sub I is going to be x sub I cosine of x sub I, which is really the pi I over 2n times cosine of pi I over 2n. Kind of gnarly looking. So then our actual limit definition here is that the integral from 0 to pi over 2 of x cosine of x, and that for now, all this really means is area under the curve. Right, that's what this symbol means for us currently at this juncture. That's going to be the limit, n goes to infinity, of the sum from I equals 1 to n of my f of x sub I, that's this here. So my pi, the pi, believe it or not, I over 2n times cosine of pi I over 2n. All that multiplied by my delta x, which is a pi over 2n. Now they might simplify this, right? They might multiply the pi's and the 2's and the n's together because they can, but I typically don't like to do that unless there's a reason to do it.
So I understand how you got pi over 2n, and then I understand the xi 0 plus I delta x, but I don't understand right below that. Why did you multiply I by pi over 2n?
Well, what's delta x? So the delta x, which is the length of your interval divided by n, is my pi over 2 divided by n, which is my pi over 2n.
Oh, you're multiplying I by this.
Exactly, yes. Other questions here? What time is it? Okay. Where to go next? Let's see. That. Yeah, I guess we need to go that way because Dell's for sure going to have you guys do that. All right, yeah. So actually, I forgot if he's going to. Usually, Dell finds a couple problems where you actually have to use this limit definition to calculate the area under a curve. Typically, I feel like it's usually in his wheelhouse. We'll do one, and we'll talk about it. We'll do an easy one to start with. In fact, one that he ended the class with, I think, yesterday. He didn't actually finish it, but the area under x squared from 0 to 1. So we are going to actually calculate the area under y equals x squared on the interval from 0 to 1. Yeah. Looks like this. So again, the idea being that we're using a bunch of rectangles. To approximate this area, and then we're taking the limit of the number of rectangles. All right, so the area here is going to equal the area under the curve from 0 to 1 of x squared dx. When you write this, by the way, I will just point out, what I'm thinking of here really is this x squared is like the height of my rectangle. And this dx is like a very, very, very narrow width of my rectangle. So there's a natural correspondence between dx in the integral notation and delta x in the summation notation. And there's a natural correspondence between f of x in the integral notation and f of x sub I in the summation notation. Because really we're just adding up areas of rectangles. And the area of rectangle is just base times height, it's base times height, right? On and on and on and on. So writing this in the limit notation, well, let's actually hold off for a second. Let's find out what our delta x and our x sub I is and all that stuff. So in this case, our delta x is going to be 1 minus 0 divided by n. Our x sub I is 0 plus I times 1 over n, which I would just write as I over n. And our f of x sub I is going to be x sub I squared, which is I over n squared, or I squared over n squared. Sorry, you can't see that. It really, if you can't see something, just tell me, yeah, James, move the paper. All right. Unfortunately, this classroom does not have the advantage of having the little screen here where I can see. Actually, technically that's not true because I can literally see the screen on my computer there, but it's not really in my field of vision, so I don't really notice it until it's too late. So, using this and this, we can say that this is going to equal the limit as n goes to infinity of the sum from I equals 1 to n of my f of x sub I, which is I squared over n squared, times my delta x, which is I over n. 1 over n, not I over n. Apologies. The delta x should never have an I in it. And now we're actually going to calculate it. So we're going to use some of those formulas that we talked about for summation notations on Tuesday. So specifically, yeah, I'm gonna move away from this page for a minute, but I'll come back to it. You definitely want to memorize these formulas, assuming that you have to actually do this. The sum from I equals 1 to n of 1 is just n. The sum from I equals 1 to n of I, 1 plus 2 plus 3 plus all the way to n, is n times n plus 1 over 2. The sum from I equals 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared plus all the way to n squared, is n times n plus 1 times 2n plus 1 divided by 6. I'm not sure if you have to memorize the last one, but I think it's so cool. I'm going to tell you anyway, because it's kind of one of the neatest things in math I think that there is the sum of the cubes is 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed. Here's a really interesting piece of information. This is equal to n times n plus 1 over 2 quantity squared. Which might not look that interesting at the moment until you look up a couple formulas. Like, oh, that's just this thing squared. So I think it is super cool that if you add up the first n cubes, it's the same as adding up the first n numbers and then squaring it. Here's what I mean. If I was to find 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, as the first example, that's going to be 1 plus 8 plus 27 plus 64, which is 9 plus 27 is 36 plus 64 is 100. But now check this out. It's the same as 1 plus 2 plus 3 plus 4 squared. And that is true as long as you start at 1, no matter what number you end up with. So it's also true, I'm not going to actually calculate it, but it's true that 1 cubed plus 2 cubed plus all the way to say, like, I don't know, 9 cubed is for sure the same as 1 plus 2 plus 3 all the way to 9 quantity squared. I just think that's super neat. Anyway, it makes it easy to memorize this last formula because this last formula is just the formula for the sum of the first n numbers quantity squared. Which I think is neat. Anyway, you don't have to think it's neat, but I think it's really neat. All right, so back to the problem we were doing. Sorry, I'm covering that up, but I'm going to cover it up for now. So what we're going to do is we say, great, this limit here, we're going to simplify it a bit. It's equal to the limit as n goes to infinity of the sum from I equals 1 to n. Let's say I have I squared times 1 over n squared times n. When you're doing a problem like this, if you have to do problems like this, you always are hoping to see powers of n in the denominator 1 larger than the corresponding powers of I in the numerator. If you're seeing that, it means you're on the road to success. Okay, now I'll remind you, last time we talked about how you could pull constants out in front of summation notation. And there is a constant there I can pull out. I know it doesn't look like it exactly, but as far as the sum is concerned, n is just some final number that is not changing. Sure, the limit's making a change, but the limit's at later. So as far as this sigma notation is concerned, n is a constant. So we're going to pull out the 1 over n cubed in front. Okay, this is equal to the limit. It's like if I was doing the sum from I equals 1 to 100 of I squared over 100 cubed. The 1 over 100 cubed is a constant I could pull out in front. The 1 over n cubed is a constant I can pull out in front. And then I have the sum from I equals 1 to n of I squared. And there's a formula for that sum. We just wrote it down. So this is going to become, that's why we're doing this, by the way, so that you can get just either the sum of I or the sum of I squared or the sum of I cubed. You're trying to make this expression look like something times a thing we know a formula for. So this is going to be the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2n plus 1 all divided by 6. Quick question. What's the limit as x goes to infinity of 2x cubed plus 5x plus 1 over 7x cubed plus 4x squared plus 3? 2 sevens. Because you know the trick that if the power on top and the power on the bottom are the same highest power, then the limit is just the fraction of the leading coefficients. Great. Right, the fraction, the quotient of the leading coefficients there. So what's the limit as n goes to infinity of this thing over that thing? Well, what's the highest power of n if you multiply out the top? Let's see, n times 2n gives me a 2n cubed. So this ends up looking like the limit as n goes to infinity of 2n cubed plus, I don't really care what comes next. I'm going to write it down anyway, but I don't actually care. It doesn't matter. Because since I know these are going to be lesser powers, they're not going to contribute at all to the limit. And the limit's going to end up equaling 2 over 6, which is 1/3. Now, I will point out that if you multiply this out, you'll get, what, let's see, 2n plus n is 3n, so 3n squared, and n times 1 is n. But those lower power terms don't matter at all. So this value, this 1/3, is actually legitimately the area under this curve between 0 and 1. Not an approximation, an exact value. Kind of neat. Eventually, not too long from now, we will bypass all of this. So I would point out, this is very, very similar to like when you learned how to take derivatives and you had to do the limit definition of the derivative of f of x plus h minus f of x all over h, and then you had to multiply it all out, cancel stuff, and factor out the h, and cancel the h, and then plug in 0. This is kind of like that step of learning integrals, where by the middle of the class, you're not doing that anymore, right? We're going to eventually learn a much more direct, or at least easier way of calculating the area under a curve using the fundamental theorem of calculus. Let me pause for questions. Let's take some water. So let's see here. What else is on my agenda? I feel like I had something else I really wanted to get to. No, not really. What's that? It is, well, it's not. So the way I got this was I ignored the n here. N times 2n is 2n squared. 1 times 2n is 2n, n times 1 is 1n, and 2n plus n is 3n. And then times n is 3n squared. Yeah, let's see here. I'm think about what to say in these last 10 minutes here. Yeah, let's do that. So that is direct. So we'll do another one of these here. Because so unfortunately, this is kind of one of the easiest examples of this, meaning they get harder. So let's look at a more kind of general example here. Yeah, let's talk about this example. So let's do the same thing. So we're gonna use the limit definition of the definite integral. That is what this thing is called. Well, the definite integral, what makes it definite is the fact that there's a lower and an upper limit of integration. To evaluate, I'm gonna write it, actually, I'm gonna do this first. The integral of, let's say, 4x plus 1. So I'll point out, without writing the limits of integration, this would be called an indefinite integral. But when you write the limits of integration, which we'll do from, let's go from 1 to 3 here. Now it's a definite integral. Definite integrals represent areas under curves. There's actually a little bit more to it than just an area under a curve. It's like a net area above, under the curve above the x-axis, but okay. And whereas an indefinite integral represents a function, an antiderivative. So we'll get there eventually. So we're going to evaluate this. So yeah, how much do I want to write here? I kind of just want to get to the chase. So I'll point out that we're going to write this as the limit as n goes to infinity of the sum of f of x sub I times delta x. That's where we're going to start. And find the usual things. So we're going to find delta x. In fact, you all should write down what delta x is. And then x sub I. And then f of x sub I. Yeah. I'm getting for delta x 3 minus 1 over n. For x sub I, I'm getting 1 plus I times 2 over n. I would always make the choice to put the I in the numerator here and write it as 1 plus 2i over n. Not required, I just feel like it's easier to write down. And then finally, my f of x sub I is going to be 4 times my x sub I plus 1. And you could simplify this. I don't think we really need to at this juncture. Putting all that together, that means we're going to be calculating the limit. Oh, I forgot my I equals 1 to n here, sorry. My limit as n goes to infinity of the sum from I equals 1 to n of my 4 times 1 plus 2i over n plus 1 multiplied by 2 over n. And then I would take the time to both simplify this as much as possible. Well, let's just, we'll do that first. So first, simplify the insides. So we're going to get the limit as n goes to infinity. Let's see here. The sum, I equals 1 to n. 4 plus 8i over n plus 1, all multiplied by 2 over n. 4 plus 1 is 5. The limit as n goes to infinity of the sum from I equals 1 to n. It's to be a pain to write that every time, but you kind of have to write it every time. 5 times 2 over n is 10 over n. And 8i over n times 2 over n is 16i over n squared. I stop and check. Do each of my fractions have a 1 lesser power of I divided by whatever power of n? Is the n squared I to the first? Check. N to the first, I to the 0th? Check. So I'm good to go. all my powers of n are exactly one larger than my corresponding powers of I. That's something you always want to make sure is true because otherwise things don't work out. Yeah. So in each of these fractions, the power of n should be one larger than the power of I that's in the numerator. So n squared I to the first, check, n to the first, and there's an I to the 0th that I didn't write there. So your power of n should always be one larger than the power of I that's in the numerator. So then we're going to break it up. So we're going to write this as the limit as n goes to infinity. I've got two things added together here, so I'm going to write it as two summations. So the sum from I equals 1 to n of 10 over n plus the sum from I equals 1 to n of 16I over n squared. And I feel like we could have probably done this step and the next step in one step. We're going to break it up and then we're going to pull out the constants. So anything that isn't an I gets to come out in front. So this whole 10 over n we're going to factor out in front, leaving behind what? What stays inside the sum? 1. And then over here, we're going to pull out the 16 over n squared, leaving behind the sum from I equals 1 to n of I. And then we throw the formulas at it. We know that the sum from I equals 1 to n of 1 is just n. And the sum from I equals 1 to n of I is n times n plus 1 over 2. So we're going to get the limit then goes to infinity of 10 over n times n plus 16 over n squared times n plus 1 over 2. Personally, I do not feel like you have to multiply this all out. Here, the n's just cancel, and you get 10. Here, if we were to multiply it out, on top, my leading term will be 16n squared. On the bottom, my leading term would be 2n squared. And so my quotient of leading coefficients would be 16 over 2. I'll point out, if you multiply this out, you get 16n squared plus 16n all over 2n squared. And the limit of that is, again, the quotient of the leading coefficients. So you end up getting 10 plus 8, which is 18. And in this case, we can check our work. What do I mean? Well, sometimes, oh man, I'm almost out of time. Okay, so let's check our work here. Here's what I mean by check our work. I can graph this. Well, yeah, I graph the other thing too. Okay, that's not a big deal. But if I graph y equals 1 plus 4x or 4x plus 1, and I'm not going to draw it as steep as it needs to be. So here's y equals 4x plus 1. If I'm going from 1 to 3, I can find the area of that shape. That's a trapezoid. Really, it's more easy if I just break it up into a rectangle and a triangle. So let's see here. This rectangle has a base of 2 and a height of, well, if I plug in 1, 4 times 1 plus 1 is 5. So this area here is 10. And this triangle also has a base of 2. And let's see, this height here, well, if I plug in 3, 4 times 3 plus 1 is 13. That was 5 there. So this height is 8. So the area of my triangle is 1/2 2 times 8, which is 8. So the area here is the rectangle plus the triangle, which is exactly equal to 10 plus 8, which is 18. Which actually brings up a really good point. Sometimes, so literally give me 1 minute. I promise you it's worth your while. Sometimes you might be asked to do something like this. Find the interval from 0 to 5 of the square root of 25 minus x squared. And you will literally be like, I can't integrate that because we don't learn how to integrate this in this class. Not something we learn how to integrate, although it is integral. It's not something we learn how to do. It requires a method called trig substitution. But you don't have to be able to integrate it because they didn't say integrate. They said find the area. And I know what shape that is. That shape, y equals the square root of 25 minus x squared, or if you square both sides, and add x squared over here, is the top half of a circle of radius 5. And so if I draw that shape, and then go from 0 to 5, I can be like, okay, well, it's a quarter of a circle. So that area is going to equal 1/4 of the area of a circle with radius 5. So 1/4 pi times 5 squared, or if you prefer, 25 pi over 4. So I should just point out that occasionally when you're asked to find the area, what they really want you to do is draw a picture of the graph and use shapes you know from geometry, like circles, triangles, and rectangles, to calculate the area. It also works really well for absolute value functions, because absolute value functions, the area usually just looks like triangles. So these are two examples. Well, that's an absolute value, and this are examples of like things you would just draw to find the area. You wouldn't actually try to get it. All right, I'm out of time. I'll see you all on Tuesday, where you'll have covered a million things by the time I see you next time. Because the Dell, right? You'll see him Friday and Monday. So